Okay, so we have done nodal analysis, which again is a streamlined version of KCL. It allows us to solve for every voltage and every current in the circuit and solve for power. So we've done several examples of that. So now we're going to move on to the other circuit analysis technique that's streamlined, that allows us to solve for every voltage and every current in the circuit. It's the second technique in this module 4A. Okay, and that's mesh analysis. And we're going to see that mesh analysis is kind of the dual of nodal analysis. So mesh analysis is a streamlined version of KVL. Okay, so streamlined version of KVL. We will write KVL equations in terms of mesh currents. Okay, so in nodal analysis, it was a streamlined version of KCL. We wrote KCL equations in terms of mesh currents, KCL equations in terms of node voltage variables. In mesh analysis, we will write KVL equations in terms of mesh current variables. And we will very shortly refer to these KVL equations from heretofore as mesh equations. Okay, so let's talk about what a mesh is. And we really already know what a mesh is, we just haven't called it this. A mesh is a loop that contains no other loops. Okay, so I have referred to those as the simplest loops in a circuit. So if we just look at a circuit in kind of a line drawing here, no elements, we just have something that looks like this, for example. And in between, all these lines represent circuit elements. This is a mesh here, so that's a mesh. This is a mesh here. This is a mesh here. These are loops that contain no other loops. Now, if you tried to do this as a mesh, okay, not a mesh, because it contains another loop. Okay, so the other thing that's important is that we have two different types of elements in our circuit structure now. This is just a structural thing. So we have elements that live on the outside of a mesh. Okay, so that would be something like an element that lives, I'm going to use the highlighter here, an element that lives here or here or here. Those sit on the outside of a mesh. So I'm just going to highlight elements in green so you know what I'm talking about. Okay, so those are elements that live on the outside of a mesh. Then we have elements that are shared between two meshes. Okay, I'm going to go back to the highlighter and I'll use yellow here. So that's like this element, this element, this element. Those are shared between two meshes, okay? And those are all the ones shared between two meshes in this particular line drawing. All right, and so these are going to be important because elements that are shared between two meshes are going to see a net difference or a net algebraic combination of two mesh currents flowing on either side. Okay, and the elements that live on the outside of a mesh here only see one mesh current. All right, so a lot of information that doesn't maybe not make a lot of sense right now. We have to go through a lot of information before we can start talking about the steps. So this is important to understand which elements we're talking about in general when we analyze a circuit element. Are they on the inside of a mesh, or shared between two meshes, or are they on the outside of a mesh? Okay, so the steps for mesh analysis are actually quite simple. Okay, there's only 3 steps really. Step 1, identify the circuit meshes. And you're going to label them with a mesh current variable. And a direction, a loop direction. Okay, now this seems odd to talk about circuit currents flowing in a loop, but it'll make sense, I think, when we get to the first, when we look at the first circuit. Okay, now, since this is, and remember, this is a streamlined version of KVL, so we always had to have a loop that we traveled in the circuit. All right, 99% of the time, I will go clockwise. There are times where it makes sense to go counterclockwise, although I rarely do that, just to be consistent. Okay. So if you like to go counterclockwise, and sometimes my left-handed students do, which is fine, it's no problem. You can go any direction you want. I will, again, 99.999% of the time, I will go clockwise. Okay, so step 2. Oh, and labeling meshes, you're going to call it I1, I2, IA, IB, whatever name, subscript convention you want to use. I typically try to use I1 and I2. Okay, I3, and so on. So step 2, we are going to write KVL equations. Okay, which, again, we are going to call mesh equations from here on out. At each loop. So for each loop, we're going to write KVL equations, and they're going to be in terms of our mesh current variables. Okay, so let's talk about the hierarchy for writing down a voltage. Okay, we did this for nodal analysis, for writing down currents. So think about these for just a second. You'll probably already know the 3 ways we can write down a voltage. Okay, so 1, is there a source? Because if there's a voltage source there, and it's not just a source, it's a voltage source. And it doesn't matter if it's a dependent or independent source. If the voltage is there, we know, if a voltage source is there, we know what the voltage is. Okay, so if there's not a voltage source, is there a resistor? Because resistors, we know Ohm's law, V is equal to I times R. Okay, where I is going to be a function of those mesh currents. Okay, if it's not 1 and it's not 2, our only other option is to label a voltage and give it a polarity. Okay, and we'll get to choose what our variable is and what polarity relative polarity we want to use. Okay. Step 3, write any other circuit rules or circuit equations as needed. And solve. Okay, so we may need another equation or 2. We saw this in nodal analysis, that sometimes we had to have other relationships in the circuit in order to have enough equations for the number of unknowns. We're going to have the same thing here. Okay, So these are the steps, okay? Now, we also have to have a rule here, because just like in nodal analysis, we didn't label current directions and voltage polarities. We did it at first, but we don't need to do that. We don't want to do that. The same thing is going to be true here. We're not going to have a bunch of voltages on the circuit so that we know whether we're adding or subtracting voltages as we go around the loop, because remember, we're still writing KVL equations. So I want to introduce you to the rule. Okay, so this is the rule for mesh analysis. Whichever mesh we are analyzing, that mesh current flows from plus to minus for the resistors in that mesh. Okay, so we're not going to have voltages labeled across every resistor. That's not the point of mesh analysis. Okay, it's to streamline that so we don't need all those variables. But we need a rule. We can't just pick which one it's going to be every time and try to keep track of that. As the circuits get bigger, we'd never be able to keep track of that to make sure that we are doing the right thing as we progress through the circuit. So we're going to have this rule. Whatever mesh we're analyzing, that mesh current flows from plus to minus. Okay, now this is going to be very important when we start talking about the difference between elements that are shared between two meshes and elements that are on the outside of a mesh. All right, so let's do a very simple circuit to start with. And we're actually going to do it just with, we're not even going to worry about solving it. This is just to get comfortable with the idea of elements shared between two meshes and elements on the outside of a mesh. So we're actually just going to write the equations. Okay, so okay, so this is V2. We're just going to put variables in here. We're not even going to worry about numbers. R1, R2, and R3. Okay, so remember, our first step is to label mesh current variables and give them a loop direction. So here's the first one. I'm going to call this one I1. Here's the second one. I'm going to call this mesh current I2. So what this means is, and this can be a little confusing at first because we usually don't talk about currents flowing in a loop, okay? So what this means is that this mesh current I1 flows through every single one of these elements in the circuit, okay, or in this mesh, all right? So an I2 flows through every single one of these elements, okay? So I1 flows through V1, R1, R3, all right? And R2 flows for R3, R2, and V2. All right, so elements that are on the outside of a mesh here, for mesh 1, for example, only see mesh current I1, okay? If we look over at mesh 2, R2 and V2 are on the outside of this mesh, and they only see mesh current I2, okay? So I1 flows through V1, I1 flows through R1, I2 flows through R2, and I2 flows through V2. And it flows in the direction that the loop is labeled. So I1 flows through here, through R1 in this direction, okay? I2 flows here, flows through V2 in that direction. Now, R3 is shared between the two meshes, and so it sees a net current of I1 and I2. All right, so let's draw R3 here. So we're just pulling it out of the larger circuit, okay? So if we look at this, we have I1 flowing in this direction, and we have I2 flowing in that direction. Okay, so the difference, or the actual net current that flows through R3 is the difference between the two because they're flowing in opposite directions. Okay, so the current through R3 is either I1 minus I2 or I2 minus I3, depending on what direction we label the current. So if we label the current in this direction, that's going to be I1 minus I2. If we label the current in this direction, that's going to be I2 minus I1. All right, but we're not labeling those currents because, again, we have our rule for how we're going to solve the voltages. Whichever mesh is being analyzed, that mesh current flows from plus to minus. So when we are analyzing mesh 1, then I1 is going to flow from plus to minus through the or across the R3 resistor. Okay, and so that's the way we will solve for our voltage with that polarity. When we move over and analyze mesh 2, we forget about mesh 1 because now we're analyzing mesh 2, and I2 is going to flow from plus to minus with respect to R3. Okay, so this is the way our circuits, the way we're going to deal with shared meshes or elements that are shared between two meshes and elements that are on the outside of a mesh. All right, so let's go to and write these equations. Okay, so let's look at mesh 1. We're going to start and end at the same point, just like we write any other KVL equation. All right, so I'm going to start down here with the V1. You choose your sign convention just like you did before. So we're just writing KVL equations just in a kind of a new way. All right, so moving from minus to plus, so mesh 1. Moving from minus to plus, I'll add V1. Coming around to R1, okay? Whichever mesh I'm analyzing, that mesh current flows from plus to minus. So I know I'm going to move from plus to minus. I know I'm going to subtract the voltage across the resistor, okay? And that current is going to be the resistance R1 times the net current flowing through it, which is just I1, because R1 is on the outside of a mesh and only sees I1, excuse me. Now, coming around to the R3 ohm resistor, shared between two meshes. So we're going to have a net current here. Okay. I still use the rule. R3, I'm analyzing mesh 1. So I1 flows from plus to minus with respect to R3. So since I'm moving from plus to minus, I know I'm going to subtract the voltage. And the voltage is going to be R3 times the current I need. The current that flows from plus to minus, I'm going to look back at this cutout that we did. Okay, the current that flows from plus to minus is going to be I1 minus I2. I'm back to where I started, and I can sum to 0. Okay, mesh 2. All right, I'm going to start at the R2 resistor here. So I'm going to start up here at this point, or at this point here. Okay, so my rule is still in place. I'm now dealing with mesh 2. I'm analyzing mesh 2. So I2 flows from plus to minus with respect to the resistors. Since I'm going to move from plus to minus, I know I'm going to subtract the voltage, and that voltage is going to be R2 times I2. R2 is on the outside of a mesh. It only sees mesh current I2. Then I come around to the voltage source. I'm moving from plus to minus through that source, so I'm going to subtract it, minus V2. Then coming back around to R3, now I'm analyzing mesh 2. So I2 flows from plus to minus, so I'm still going to subtract the voltage, which is going to be R3, but now I need the net current that flows from plus to minus on the I2 side, so that's going to be I2 flows from plus to minus, I1 flows against. So this net current is going to be I2 minus I1 is equal to 0. Okay? So let's take a look at these and see if we can find some interesting facts about these mesh equations. If we look, and I did this for nodal analysis too, although I think this is more obvious. If we look at our mesh currents, our mesh equations, whichever mesh we're analyzing, the voltage drop across the resistors are always either going to be subtracted or added, depending on whether you're doing the passive or active convention. So if you're doing the active convention like me, the voltage drops across your resistors are always going to be subtracted. Okay? So if you're doing the passive convention, they're always going to be added. All right, and when you subtract the voltage is always the resistance multiplied by the current. If and it's the current, the mesh current that we're analyzing minus the current flowing on the other side. Okay, so for resistors on the outside of a mesh, there is no current flowing on the other side because they're on the outside of the mesh and only see one current. So you can look at these as I1 minus 0, I2 minus 0. For the shared elements, it's always the mesh current we're dealing with minus the current flowing on the other side. That's true as long as all of your mesh currents are in the same direction, clockwise or counterclockwise. A lot to take in all at once. Let's do a few more examples and see if we can make this work. Now, I will tell you, most students, and I've taught this course for 100 years, most students prefer mesh analysis over nodal analysis. Mostly because you're not dealing with fractions, but this method tends to resonate with students. So if nodal analysis was tough for you, you might find this to be a little bit more straightforward. Okay, so let's look at a very basic circuit. This was very similar to the basic circuit we did for nodal analysis, our first circuit there. Okay. So what we're going to do here is we're going to solve for the mesh currents and then use those to find the power delivered and absorbed by every element. Okay, so we did a similar activity for nodal analysis. We're going to do the same thing here for this circuit for mesh analysis. Okay, now if you recall in nodal analysis, we talked about writing down things that we know to get started with. And in nodal analysis, when we first started, there wasn't a lot of things that we knew yet. That's going to be different for mesh analysis. We tend to know some things by just looking at the circuit and getting started. All right, but let's first start by labeling some mesh currents. So I'm going to label one here. I'm going to call I1, and I'm going to label one here, and I'm going to call it I2. Okay, so whenever you have a current source in the circuit, you know something about the mesh currents. You might know a mesh current, or you might have a relationship between mesh currents based on that current source. So I2 is the current that flows through this mesh. So the 4 ohm resistor sees both I2 and I1, but the 2 amp source is on the outside of a mesh and it only sees mesh current I2. Also, I2 in this particular circuit happens to be flowing in the same direction as the source. So we know that I2 is equal to 2 amps. Okay, so we know that right off the bat. Okay, and that's all we know about this particular circuit before we even get started writing mesh equations. Okay, so just like in nodal analysis, when we did a couple of examples where we knew what the node voltage was, we didn't have to write a nodal equation in order to solve for the other node voltages in the circuit. Same thing here. If we know I2, we don't need it to solve for I1, or we don't need an equation for mesh 2 in order to solve for I1, the mesh current I1. So we are only going to need the mesh 1 equation. Okay, so the mesh 1 equation, I'm going to start with the source. Moving from minus to plus, I will add 10. Coming around to the 6 ohm resistor, remember my rule, whichever mesh I'm analyzing, that mesh current flows from plus to minus. So I know I'm going to subtract the voltage, and it's going to be 6 times I1. Okay, it's on the outside of a mesh, only sees mesh current I1. Coming around to the 4 ohm resistor, I1 flows from plus to minus, so I know I'm going to subtract the voltage. And the voltage is going to be 4 times the net current that flows from plus to minus. That's going to be I1 minus I2. Back to where I started, I can sum to 0. Okay? So I can substitute in that I2 is equal to 2 amps. Okay, so when I do that, I can solve. I'll have one equation, one unknown, and I can solve for I1. I'm going to have minus 10 I1 is equal to minus 18, or I1 is equal to 1.8 amps. Okay, so we know I1 and we know I2. I2 we knew just by looking at the circuit after we labeled the mesh currents, and I1 we solved for using the mesh 1 equation. Okay, so let's go ahead and solve for some, and let's write down that right now, mesh 2, we don't need a mesh 2 equation. Okay, we know what I2 is. We do not need a mesh equation right now. Okay, we didn't need it to find I1. So let's look and see what this takes us now, because we want to solve for power delivered by the sources and absorbed by the resistors. So let's start with the 10-volt source. So P is equal to V times I. Okay, so the voltage is the value of the source, 10. Okay, and what is the current? Well, I1 is the current that flows through the 10-volt source. It flows in this direction, so it is flowing from minus to plus. So it's flowing in the quote-unquote right direction to give power delivered. So this is just going to be 10 times I1, or 18 watts. And this is delivered because that mesh current I1 flows from minus to plus with respect to the 10-volt source. Okay, now let's look at the 2 amp source. P is equal to V times I. What's the voltage drop across the 2 amp source? Well, we don't know. We don't know what it is. Okay, we have to solve for it here. And this is why we're going to now write that second mesh equation. Okay, we did this with nodal analysis too. All right, for when we had a voltage source isolated between 2 nodes. Here we have a current source, and we're going to have to do the same thing. Now, the difference is here, the current source doesn't have to be isolated between 2 nodes, but in this circuit it is. Okay, so in order, we need V, okay, and we don't have it yet, so we're going to have to find the mesh 2 equation to get this voltage. So let's write the mesh 2 equation. Okay, so I'm going to start with the 4 ohm resistor. Okay, it is shared between 2 meshes. The mesh current, the mesh I'm dealing with, that mesh current flows from plus to minus. I know I'm going to subtract the voltage. That's going to be 4 times I2 flows from plus to minus because of the rule. I1 flows against. So that's going to be minus 4 times I2 minus I1. Coming around to the current source, let's ask ourselves the hierarchy here. Is there a voltage source there? No. Is there a resistor? No. So our only other option is to label a voltage variable with a reference. And since I'm going to need to solve for power delivered, I'm going to label my voltage reference here. I'm going to call it VS and give it a polarity such that I'm getting power delivered. Okay? Could you have done it the other way? Reverse that polarity? Picked a different voltage variable? Absolutely. Okay, so coming around now, I'm going to move from, so I'm coming this way. I'm going to move from minus to plus, so I'm going to add VS. And then I'm back to where I started, and I can sum to 0. I know I1 and I2, so I can solve for VS, and I'll get that VS is equal to 0.8 volts when I substitute in I1 and I2. So now, P is equal to, for the 2 amp source, P is equal to the voltage VS times 2, and that's going to be 1.6 watts. And that's delivered because the current is flowing from, the current is flowing from minus to plus. Okay? And I should add this in up here, power. All right. So we have the power for the sources. Let's talk about power for the resistors. Okay, since we are solving for currents in mesh analysis, I tend to use I squared R for power for resistors, although you do not have to. Certainly you can solve for voltage if you want to. So I'm going to use P is equal to I squared R. All right, let's look first at the 6 ohm resistor. So pulling back up to this circuit here, the 6 ohm resistor is on the outside of the mesh. It only sees mesh current I1. We don't care which direction I1 is flowing in, right? Because since we're going to square the current, it doesn't matter to us. We don't have to worry about voltage polarities, relative current directions. All we need is the value of the current because we're going to square it, and we know that the power associated with the resistor is absorbed. That's the beauty of using the I squared R or V squared over R. So P is equal to I squared R. I in this case is I1 squared. We'll multiply it by 6. And when we substitute I1 in, we'll get 19.44 watts. And this is absorbed because resistors only absorb power. Okay, let's go to the 4 ohm resistor. Now the 4 ohm resistor is may seem more complicated because it's shared between 2 meshes, right? And so its net current can be I1 minus I2 if that net current is flowing in this direction, or I2 minus I1 if that net current is flowing in that direction. But it doesn't matter to us, right? Because we're going to square it. So it doesn't matter which current we choose, which net current we choose. So I can write this P as either being I1 minus I2 squared over 4 or I2 minus I1 squared over 4. Okay, either one of those will give us the same answer, which is again the nice thing about using I squared R or V squared over R. We don't care. We don't care if the sign on either one of these currents is negative. We don't have to worry about passive sign convention because we're going to square that current. Now, if we're actually solving for current or solving for voltage, then it matters. But for power, doesn't matter. So when we choose whichever one of these we want to, we're going to get that this is equal to, and I wrote over 4. Let's fix that. I'm sorry. I had voltage on the brain. Let me fix that. Sorry. I1 minus I2 squared times 4 times 4. So either one of those. I squared times R. My apologies. Okay. Please make sure that you're noting this. So now, P is equal to 0.16 watts absorbed. Okay, so the sum of the power delivered is equal to 18 plus 1.6 from the sources, so that's 19.6 watts. Sum of the power absorbed is equal to 19.44 plus 0.16, which is equal to 19.6 watts. And of course, this makes us very happy because everything is working out. Okay, let's do another example. I'm going to move to a new page. Okay, so this is our circuit. We're going to do the same thing we did for the first circuit. We're just going to solve for all the mesh currents and then find the power delivered. No, we're going to find the power delivered by each element, or delivered or absorbed by each element. Is that what we're doing? Please hold. No, here we're not going to do that. We're going to actually solve for some things. Okay, so we're going to solve for this voltage here. I'm going to call this voltage Vx, and we're going to solve for this current here. We're going to call that current Iy, and I'm going to go over these in blue so we can see them a little better. Okay. So we're going to find the mesh currents and then find those two elements, voltage and current. All right, so let's label some mesh current variables. Here's I1. Here's I2. Here's I3. Okay, and like I said, I'm almost going to always label those in the clockwise direction. Okay, so let's start off by writing down things that we know. So what do we know? Well, if we look at mesh 1, we have I1 flowing through a current source, okay? Anytime we have a current source, we know something about the circuit, okay? So in this case, I1 flows in the direction of the 5 amp source, so we know that I1 is equal to 5 amps. Now you might be saying, what if I1 flows opposite to the direction of the current source? Then I1 will be minus the value of the source, okay? So if that what your instinct was, your instincts are spot on. All right, it also helps at this point to write down what we're solving for, okay? So we're going to solve for Vx and we're going to solve for Iy. So let's write these down in terms of our mesh current variables if we can, okay? So, so here we, Vx. So Vx, we're writing Ohm's law now, so you have to separate the technique of mesh analysis and coming up with expressions for these voltages and currents, okay? So Vx is just the voltage drop across the 4 ohm resistor, all right? That implies that we need a current flowing in that direction, so it's flowing from plus to minus with respect to that voltage through the 4 ohm resistor. So what current flows in this direction? Well, I2 flows in this direction, so minus I2 flows in the opposite direction. So we're just adjusting for the passive sign convention here. So Vx is equal to 4 times minus I2. Okay, so now let's talk about Iy. So Iy is this current here, okay? I2 flows on one side, I3 flows on the opposite side with those directions. So Iy is equal to the current flowing in the direction we want, so I2, minus the current flowing against it, which is I3. So IY is equal to I2 minus I3. Okay, so now we're going to go on and write the mesh equations that we need. Once we have written down Vx and Iy, we don't need those voltages and currents labeled on the circuit in order to solve. And I find that if you leave them there, this can be very confusing for you, especially at first. So what I'm going to do is I'm going to take the circuit and I'm going to copy it. I'm going to try to copy it. And I'm going to paste it down here. And what I'm going to do is I am going to get rid of this voltage and this current. I don't need it to solve for the circuit now. I need it eventually to solve for the to solve for them. I need these relationships, but we've already written them down. You do not need those currents and voltages to write the mesh equations. Okay, and I want to go through this without those on the circuit, erase them, draw the circuit again. And as you get more comfortable with this, you'll see that you don't really need them, and you don't need to erase them either. You can just ignore them for the purposes of the technique. Okay, so mesh 1, do we need a mesh 1 current or a mesh equation? We don't, because we already know that I1 is equal to 5. So we don't need this. Okay, you might need it. We had to write it down to solve for power. Let's scroll back to that original circuit here. We needed to write that mesh equation eventually to solve for power associated with that current source. We're not solving for power here for the 5 amp source, so we're not going to need that mesh equation ever for the purposes of this particular problem. All right, so don't even bother to write it down, because I find that when you write equations down, you tend to want to use them even if you don't need them. Okay, and that can complicate your math and get you confused, and then you end up struggling. Okay, so we don't need mesh 1. Mesh 2, I'm going to start with the 4 ohm resistor at the top. So remember the rule, whichever mesh current we're analyzing, that mesh current flows from plus to minus. So since I write the active convention, I know I'm going to subtract the voltages across all the resistors. So starting with that 4 ohm resistor, I'm going to subtract the voltage, and it's going to be 4 times I2, because 4 ohms is on the outside of a mesh, only sees mesh current I2. Coming around to the 5 ohm resistor, shared between 2 meshes, I'm going to subtract it. It's going to be 5 times the mesh we're dealing with, I2, minus the mesh current flowing on the other side, I3. Okay, coming down to the 6 volt source, moving from minus to plus, I'll add 6. Then coming around to the 2 ohm resistor, okay, so I'm over here now. All right, moving from, or I know I'm going to subtract the voltage, and it's going to be 2 times the current I'm dealing with minus the current flowing on the other side. And I'm getting kind of closed in here. Let me move this over. And that sums to 0. I'm back to where I started. I can sum to 0. Okay. Mesh 3. I'm going to start with the 6 volt source. Okay, so moving from minus to plus, I'll subtract 6. The 5 ohm resistor, I'm now analyzing mesh 3. So I3 flows from plus to minus, so I'm going to subtract the voltage, and it's going to be 5 times the mesh I'm dealing with minus the mesh current on the other side. So I3 minus I2. Coming around to the 1 ohm resistor, I'm going to subtract 1 times I3. The 1 ohm resistor is on the outside of a mesh, only sees that mesh current, I3. Back to where I started, I can sum to 0. Okay, remember that we know that I1 is equal to 5. We wrote that down at the top there. All right, so I can substitute 5 into this expression, and I'll have 2 equations, 2 unknowns in terms of I2 and I3. And I'm going to write those equations down for you. So mesh 2 is going to simplify down to minus 11 I2 plus 5 I3 is equal to minus 16. And mesh 3 is going to simplify to 5 times I2 minus 6 times I3 is equal to 6. And when we're done, we'll have I2 is equal to 1.61 amps, and I3 is equal to 0.341 amps. I'm going to grab these and bring them down. So remember what we were solving for ultimately? We were solving for Vx and Iy. So we will have, we will have Vx is equal to minus 4 times I2. And that will be minus 6.44 volts. And then Iy is equal to I2 minus I3. And that is going to equal 1.27 amps. Now, I would encourage you to take this problem and try to solve for the power delivered by each source and absorbed by each resistor and see if you can make that work out. You're going to end up having to write that first mesh equation for the 5 amp source in order to get its voltage. Okay, so give that a try. All right, so the rest of the mesh analysis problems we are going to work as problems in the example. So this will get you started, and look to the example lecture for, we'll do probably 3 or 4 more examples. Okay.